Can you hear me? Hello. Am I audible to you? Okay, Agarsh. Okay. Okay. So please tell others to join fast. Okay. I'll share my screen now. Hope you can see the screen. Okay, Agarsh. Okay. So last class, what did we discuss in last class? What did we discuss in last class? Do you remember? Given a lattice, we check. Given a Hesse diagram, we check whether it is a lattice or not, isn't it? And how did we check whether it is a lattice or not? We had to write all possible combinations of elements in the lattice. See, that is what is shown here. You have to write all possible ordered pairs in the lattice and check if it has a least upper bound and a greatest lower bound. If it exists for all ordered pairs in a lattice, then it can be in a Hasse diagram, then it can be considered as a lattice. All Hasse diagrams are not lattices, but all lattices are Hasse diagrams. So given a Hasse diagram, you will be asked to check whether it is a lattice or not. So to check whether it is a lattice or not, you have to write down all the ordered pairs, all possible ordered pairs in the Hasse diagram, and then you see here we have taken all possible ordered pairs here and find out for each ordered pair you have to find the least upper bound and greatest lower bound. If it exists for all ordered pairs, then we can call it as a lattice. Okay, it is called a lattice. Then, now we are going on to the next section, distributive lattice. Okay, the next section, very important section, distributive lattice. After covering distributive lattice, we will come to other types of lattices. Now, what is a distributive lattice? Did all of you join? Very important question. You have to write it down in your notebook as I'm explaining. Okay. And also these notes are uploaded in Linways also as solved examples on lattices. So in Linways, I'd given the heading solved examples on lattices. Go to that notes, take that notes, and you will be getting all the different possible lattices and how you can identify whether it is a lattice or a not. And every question is solved and uploaded there. So let us see what a distributive lattice is. Distributive lattice. So a distributive lattice is one that satisfies both the distributive laws. A distributive lattice is a lattice that satisfies a lattice that satisfies both the distributive laws, both the distributive laws, both the distributive laws. Now, what are these distributive laws? We had studied earlier what distributive law is. That is A and B or C is equal to A and B or A and C. This is the first distributive law. You have two distributive laws, isn't it? Second one is A or B and C, the dual of this. A or B and C is equal to A or B and A or C. So these are the two distributive laws, and a lattice that satisfies both these distributive laws is called a distributive lattice. Now here in a lattice, we studied what this and or means. What do you call these symbols in a lattice? What are these symbols in a lattice? What do you call these symbols in a lattice? We call it as meet and join, isn't it? And is called meet and or is called join. That is the meet is the greatest lower bound and join is the least upper bound. This is the greatest lower bound, GLB or meet, and join is the least upper bound. Okay, so here if we take any three elements in the Hesse diagram, and if we try to find out whether this property is satisfied, then, and if both the properties are satisfied, 1 and 2 are satisfied for any three elements in a lattice, and likewise if you are taking all possible three combinations in a lattice, and if you are trying to find out if the distributive law is satisfied, then we say that it is a distributive lattice. So the definition goes like this. Okay, a lattice that satisfies both the distributive laws is called a distributive lattice. And there are two distributive laws. These are the distributive laws. So if you are asked to if you are asked to define what distributive lattice is, you have to write the definition and write these two distributive laws. And a lattice that satisfies both these laws are called a distributive lattice. Now let us look at an example whether now of how to find whether given a lattice it is distributive or not. Is it clear? Did you understand what I said now? What is a distributive lattice? 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 Yes, a lattice that satisfies the distributive laws is called a distributive lattice. And all lattices will not satisfy these distributive laws. Only certain lattices will satisfy the distributive laws. Yes. So those that satisfy the distributive laws are called distributive lattices. So we find that all lattices are not distributive. Only if we only after checking these distributive laws, and if it satisfies on that lattice, then we call it as a distributive lattice. Now let us see some of the examples of distributive lattices. Okay. See, this is distributive lattice. See, a lattice which satisfies the distributive property is called distributive lattice. So here we have A or B and C is A or B, and this law we are studying from module 1 onwards, isn't it? So this is called the distributive law, and if the distributive law is satisfied in this lattice, then we call it as a distributive lattice. Now let us see how it is done. So write this down and draw this diagram. Okay, you can write along with this. Write the heading as distributive lattice, write the definition and the laws. Now draw this figure. Check whether the and write a question. Check whether the lattice shown below is a distributive lattice or not. Very important question. Okay. Now to check whether this is a distributive lattice, what we have to do is we have to take all possible three. Now here in this distributive lattice, how many elements are to be considered at a time? How many elements should we choose at a time? We need A, B, and C. So three elements should be considered from the lattice. Three elements are to be taken, isn't it? Three elements are to be taken. So how many possible combinations of three elements will be there from this lattice? How many possible combinations of three elements? How will you find out the combination of three elements from four? How many possible combination of three elements will be there in this lattice? There are total how many? Total four elements, isn't it? How many elements? Total there are four elements in the lattice, one, two, three, and four, out of which I'm going to take three at a time. So what are the different combinations? Can anyone say? We had studied permutation and combination and all. So There are four elements in the lattice, and I'm to take three elements at a time. So, what are the different possible combinations? How many different possible combinations I will get? How many different possible combinations I will get? What are the different combinations? Nobody is answering now. What are the different combinations that I can get from four elements taken three at a time? Yes, 4C3. What is 4C3? Find the value of 4C3. Very good, Niharika. What is 4C3? What is the value of 4C3? Yes, 4. Isn't it? 4C3 is 4. So, how will you write the combinations, different combinations from this? There are four combinations. What are those four combinations? For those four combinations, we have to check if these two laws are satisfied for all the four combinations. So it is, as Niharika said, it is 4C3. Take 4C3, and 4C3 is equal to 4 factorial by 4 minus 3 factorial into 3 factorial. When you evaluate it, 4 minus 3 is 1 factorial, which is 1, and this 3 factorial will cancel here. That is 4 into 3 factorial. So you get finally the number of combinations is 4. You have total of four combinations here, and the combinations for each of them, for each of the combination, we have to check if if it satisfies the distributive law. So let us see what are those four combinations. The first combination is 1, 2, 3. See, the first combination is 1, 2, 3. Then the second combination is 1, 2, 4. The third combination is 2, 3, 4. And the fourth combination is 1, 3, 4. So these are the four possible combinations. And for all these four possible combinations, what we have to do is we have to find out, we have to check if it satisfies the distributive property. So the different combinations include, just write the four combinations, that is 1, 2, 3. Then you have 2, 3, 4. 1, 2, 4. 1, 2, 3. 2, 3, 4. 1, 2, 4. And next is one more combination is there. 2, 3, 4. 1, 2, 4. And one more. 1, 2, 3. They have 1, 2, 4. Then 2, 3, 4. And last one is 1, 3, 4. Oh, it's 1, 3, 4. 1, 3, 4. Okay. These are the four possible combinations. Now, for each of these combinations, we have to check whether these two laws, 1 and 2, are satisfied. Both laws are satisfied. Likewise, you have to check whether it is the both laws are satisfied for these this combination. Again, the two laws should be checked. Again, here also you have to check the two laws. So if the law is satisfied for all, then we say that it is a distributive lattice. Now let us take the first combination, 1, 2, 3. Okay, 1, 2, 3. Now what we are going to check? We are checking whether the distributive law is satisfied. See, from 1, 2, 3, let us see the first law. So this is A, this is B, and this is C. So A or B and C is equal to A or B and A or C. So let us look at the left hand side first. That is A or B and C. A or B and C. And that is 1 or 2 and 3. What do you get? 1 or 2 and 3. What is 2 and first we have to compute 2 and 3. What is 2 and 3? This is 2, this is 3, and 2 and 3 means this and here implies what? What does this and imply? It implies the meet of 2 and 3. Meet means what is meet? The least upper bound of 2 and 3. Now the least upper bound, sorry, the greatest lower bound, isn't it? Meet means the GLB, greatest lower bound. Okay. Meet is the greatest lower bound. So GLB. So the greatest lower bound of 2 and 3 is 1. So here this evaluates to 1. So 1 or 1. 1 or 1 means, this means the least upper bound. This is join, so it is least upper bound of 1 or and 1. So the least upper bound of 1, upper bound of 1 includes 2, 3 and 4, 1, 2, 3 and 4, and the least upper bound of 1 is 1. So this side, the left hand side evaluates to 1. Now let us see what the right hand side evaluates, that is A or B and A or C. So this is A is 1, B is 2. So A 1 or 2 and 1 or 3. 1 or 2. What is 1 or 2? What is 1 or 2? This is 1, this is 2. And 1 or 2 means, what is 1 or 2? This is the, what? This is a join, isn't it? What is join? Join of 1 and 2. Join of 1 and 2 is, join means the least upper bound. Join is least upper bound. So the upper bound of 1 and 2 is 2 and 4. So the least upper bound is 2. So that 2 is here. Then next and. Next is 1 or 3. 1 or 3 means, what is 1 or 3? This is 1 and this is 3, and 1 or 3 means the least upper bound of, the least upper bound of 1 and 3. Upper bound of 1 and 3 is 3 and 4. The least upper bound is 3, isn't it? So it evaluates to 2 and 3. And what is 2 and 3, or 2 meet 3? 2 meet 3. 2 meet 3 means the greatest GLB, the greatest lower bound of 2 and 3. 2 and 3, it has a lower bound 1, and the greatest lower bound is 1. Greatest lower bound of 2 and 3 is 1. So the LHS is also evaluated to 1, and the RHS also evaluated to 1, which means the first law is satisfied. Okay, for this ordered pair, we have found out that the first distributive law 1 has been satisfied. Next, what we have to do is, we have to check for the same ordered pair 1, 2, 3. We have to check if the second distributive law is satisfied. Okay, for the same ordered pair 1, 2, 3, we have to check if the second distributive law is satisfied. That is, 1 or, see the second distributive law, 1 or 2 and 3, isn't it? If you have checked the first law, next we have to check 1 and 2 or 3. See, this is the second law, 1 and 2 or 3. The second law. Here we have to check the second law, that is 1 and 2 or 3 is equal to 1 and 2 or 1 and 3. So this is the LHS and this is the RHS. So you have to check whether the LHS evaluates to RHS. So 1 and 2 or 3. Again, look at the figure and find out what is 1 and 2 or 3. 2 or 3 means the join of 2 and 3, that is the least upper bound of 2 and 3. The least upper bound of 2 and 3 is 4, isn't it? It has only one, 2 and 3 has only one upper bound, and that is 4. The least upper bound is 4. And 1 and 4. 1 and 4 means the meet of 1 and 4. The meet means the greatest lower bound of 1 and 4. The greatest lower bound of 1 and 4 is 1. So, likewise, we have to evaluate the entire formula and find that the two distributive laws are satisfied. So, this we had checked only for the first ordered pair, isn't it? First set of first combination, that is 1, 2, and 3. Likewise, we have to take the next one, 1, 2, and 4. Take the next combination 1, 2, 4, and again check if the two distributive laws is satisfied. That is 1 or 2 and 4 is equal to 1 or 2, 1 or 2 and 1 or 4. You have to check this law, and for that you have to find the LHS and RHS, and if they evaluate to the same, then the first law is satisfied. Then again you have to check whether 1 and 2 or 4 is equal to 1 and 2 or 1 and 4. Now, again, you evaluate this RHS, LHS, and then this RHS. And if these two are again equal, then we say that the second distributive law, this is the first distributive law, second distributive law is also satisfied for 1, 2, and 4. So that ordered pair is also, we find that or it is satisfied. Okay, for this lattice, it is satisfying. Likewise, you take the third ordered pair. Okay, the third ordered pair is 2, 3, 4. For again 2, 3, 4, you have to check whether 2 or 3 and 4 is equal to 2 or 3 and 2 or 4. This is the first distributive law. And you again look at the lattice and find out the meet, and that is the greatest upper bound and least GLB, that is greatest lower bound and the least upper bound, you have to find out and then substitute and see if they are equal. And again, you have to check for the second law is also satisfied for that combination, that is 2 and 3 or 4 is equal to 2 and 3 or 2 and 4. So this is the second distributive law. So for this 2, 3, 4 combination also, you have to check if first distributive law is satisfied as well as the second distributive law is also satisfied. So here we have to look at the lattice and find out the meet and join. That is the least upper bound and the greatest lower bound, and substitute in this. And so finally you should get that these two sides are equal. Only then the distributive law will be satisfied. The LHS should be equal to RHS. So we find that it is, if they are equal, then the distributive laws are satisfied. So next we have to go to the last combination, and again the same process is repeated. The last combination is 1, 3, 4. The last combination is 1, 3, 4 in the lattice. So you have to check 1 and 3 or 4 is equal to 1 and 3 or 1 and 4. This is the first distributive law. Second distributive law is 1 or 3 and 4. Just the dual of the first one is equal to 1 or 3 and 1 or 4. And again, you have to look at the lattice and find out the meet and join and all of these two elements. And then you have to substitute and find that this LHS is equal to this RHS. If they are equal, then again the second distributive law is also satisfied. Here these are equal, then first also satisfied for this combination 1, 3 and 4. So likewise, if all combinations satisfy both the distributive laws, then we say that it is a distributive lattice. Now for this, when we evaluated, we found that all are equal. Okay. All these are equal, and so this distributive property is satisfied for all the combinations in the lattice, and hence we call it as a distributive lattice. Is it clear? Do you know how to check whether it is a distributive lattice or not? This is solved and I had uploaded this. Okay. Do you know how to check a distributive whether a given lattice is a distributive lattice or not? Did you understand? Hello. How do we check whether a given lattice is a distributive lattice? What is a distributive lattice? What is a distributive lattice? Why you are not responding? What is a distributive lattice? Hello. Yes, that satisfies distributive law. And how do you check if it is a distributive lattice? How do you check if it is a distributive lattice? Now come on fast, otherwise my time is getting wasted. How do you find whether it is a distributive lattice or not? Given a lattice, you have to take all possible three combination, isn't it, of the elements in the lattice. And we need three combination because to check distributive law, we need three elements, isn't it? A, B, and C. That is A or B and C is that formula. That formula goes like that. A or B and C is equal to A or B and A or C. So to check the distributive law, we have to take three elements at a time from a lattice, and all possible three combination of elements should be taken from the lattice. So if a lattice has five elements, how many combination of elements should you check? If a lattice has five elements, how many combinations should you check? A lattice has five elements, how many combinations should you check? Both the distributive laws should be satisfied for all combinations. So how many combinations will be there if there are five elements in a lattice? Come on fast. If there are five elements in a lattice, if a lattice has five elements, how many combinations will be there? How many combinations should you check? A lattice has five elements. How many combinations? 5C3, very good. 5C3 combinations of elements should be there. And what is 5C3? 5 factorial by 5 minus 3 factorial into 3 factorial, isn't it? That is equal to 5 factorial by 5 minus 3, 2 factorial into 3 factorial. What do you get? 5 into 4. This 3 factorial will get cancelled here by 2. 10 combinations, isn't it? For each of these 10 combinations, you have to check whether both the distributive laws are satisfied. So usually we give only a very small number of elements, and also if for any one ordered pair, if it does not satisfy, then you can stop with that. Okay, you needn't proceed further. If for any combination of the lattice, if it is not satisfied, then we can stop with that and we can say that you needn't check all the 10 ordered pairs. Just if the first, if you're, when you're evaluating the property, or when you're verifying this property, if it is not satisfied for the second ordered pair, second set of elements, then you can stop with that and say that it is not distributive, since distributive law is not satisfied for these elements. So let us see some examples, some more examples. So other examples are solved here. See, another lattice is also given here. Okay. So you have to remember one more thing here in a lattice. The lowest element in a lattice is often 0, and the highest element is often the identity element I. For any set, the highest element will be the entire set of elements, the lowest element will be the empty set null. So that's why here in a lattice also the lowest element is the 0 and the highest element will be 1. And here the possible combinations are A, B and C are the actual elements here. Okay, so with these five combinations, you have to check whether it satisfies distributive law or not. Take the different combinations and check if it is distributive or not. So consider 0AB, then 0AC, and it goes on like that. Okay, take all the ordered pairs, all different combinations of ordered pairs, and for this property we find that this if for when we take ABC, we find that the distributive law is not satisfied. So the distributive, if it is not satisfied, then it is not a distributive lattice for any particular combination. If the distributive law for this combination, the distributive law is not satisfied in this lattice. So see, this is not satisfied. So we say that it is not a distributive lattice. Okay. So let us see some more examples. So next example, the one which we had seen earlier. Let us see that that is A, B, C. Same example. Let us see why it is not satisfied. This is 0, this is I. Okay. So here I'm taking these elements A, B, and C. That is A and B or C. Distributive law. According to distributive law, A and now once this is given, you can just take the given elements first and then you go for 0 and 1. Okay. The easiest way is if you're given three elements and this I and O you can take at the end. You first take the element combinations, the middle element combinations or the elements to which I and O are connected. So first check those elements first. So if it is not distributed, this will turn out to be not equal. So A and B or C is equal to A and B or A and C, isn't it? This is the first distributive law. Now check if what is whether this is satisfied or not. Now let us evaluate this LHS first, and then we will evaluate the RHS. Now what is B or C? What is B or C? B or C means what is B or C? What is B or C? Anyone? What is B or C here? What is OR? OR means join, isn't it? What is join of B and C? Least up join means least upper bound. So what is the join of B and C? The upper bound of B and C is I. Only I is there. So the least upper bound is also I. It has only one element as its upper bound. B and C has only one element as its upper bound, and that is the least upper bound. So B or C evaluates to I and A and I. What is A and I? What is A and I? This is A, this is I. And A and I means and means the meet. Meet means the greatest lower bound. Now, what is the greatest lower bound of A and I? I, A. The lower bound, the greatest, it has only one lower bound, isn't it? It has the lower bounds includes A because you have to check less than or equal to, the lower bounds includes A and 0 and the greatest lower bound is A. Okay, so A and I evaluates to A. Now this is the LHS. LHS evaluated to A. Now let us see what is RHS. RHS, A and B. A and B. This is A and B means what is A and B? A and B means the meet of A and B. The greatest lower meet is the greatest lower bound of A and B. Meet means GLB. So greatest it has only 0 as its lower bound and the greatest lower bound is also 0. Or now what is A and C? A and C. That is the meet of A and C. That is the greatest lower bound of A and C. Again, it is 0. So 0 join 0. 0 join 0 is 0. So this RHS evaluated to 0 and the LHS evaluated to A. So this is not equal. RHS is LHS is not equal to the RHS. The first distributive law itself is not satisfied. In this lattice, when we consider A, B, and C, the first distributive law itself is not satisfied, isn't it? Hence, since this law is not satisfied, we can say that it is not a distributive lattice. Okay, so you can just take the combination, check the first law. When we check the first law itself, we found that the distributive property is not satisfied. The two sides are not equal. And from this itself, we can conclude that it is not a distributive lattice. Is it clear? So you needn't go for all combination, all 10 combinations. You can just find out, choose three elements, three combination from this, and whenever we find that a distributive law, either first law or second law, if it is not satisfied, then we can stop and say that it is not a distributive lattice. Is it clear? Is it clear? Did you understand what a distributive lattice is? Just write this down, okay? Any doubt in this? Hello? Okay, so let us see another example, okay? See, draw this example also. The least element in the lattice is designated as O and the top element is I. So check if it is a distributing lattice. How do you check if it is a distributing lattice? Is it a distributing lattice? Check if it is a distributed lattice. How will you check whether if it is a distributive lattice or not? You have to take the you have to check the distributive law for three combination elements. So instead of taking I and O first, you can take the given elements first. Okay, always take the given elements first. So first combination, let us take A, B, and C and check if distributive law is satisfied. Just can you check and see if distributive law is satisfied? Take A, B, and C and check. Instead of I and O, you can take the given elements first and check if distributive law is satisfied. Check if it is satisfied. Is it satisfied? Can you take A, B, and C? What is the first distributive law? A and B or C, isn't it? Is equal to A and B or A and C. This is the first distributive law. Now for this lattice, you just find out the meet and join of these elements. What is A and what? Now here we have to check first B or C. What is B or C? This is B, this is C. B or C. That means the greatest upper bound, isn't it? Join of B and C. The greatest upper bound, B has upper bound I, and C also has the common upper bound I. So B, for the greatest upper bound of B and C is I. B is not related to A. B has the upper bound I and C also has the upper bound I. Since if C is related to A and A is related to I, then there is a direct edge here which we had eliminated in the assay diagram. So for B it is I and C also it is I. So B greatest upper bound is I. So A or A and I. Now what is A and I? That is the greatest lower bound of A and I. The lower bounds of A and I include A, C, and O, out of which the greatest is A. So here you will get A. This is the RHS. RHS evaluates to A. Now, what is LHS? You have to evaluate LHS, that is A and B. This is A, this is B, and the greatest lower bound of A and B. So here the greatest lower bound is 0. B is not related to C, but A is related to uh, B is related to 0 and A is also related to 0. So the least upper bound is 0 or an A and C. And for A and C, the least upper bounds include C and 0, and so out of which the greatest lower bound is C, and 0 or C, 0 or C. And the greatest upper bound of 0 or C is C. The upper bounds of 0 or C is C, A, and I, out of which the greatest upper bound is C. So we find that A is not equal to C. RHS evaluated to A and LHS evaluated to C. They are not equal. So distributive property is not satisfied, isn't it? Since distributive property is not satisfied, the first law itself is not satisfied when we take A, B, and C for this particular lattice. This lattice, it is a lattice, but it is not a distributive lattice. Not a distributive. It is a lattice, but it is not a distributive lattice since distributive property is not satisfied. Is it clear? Did you understand what a distributive lattice is? Did you understand what a distributive lattice is? Hello? Okay. Okay, Akash. Okay, Anurag. Only two are responding. I think I'm teaching only two people at a time now. Now say your attendance.
1,
2, 3,
4, 5,
6,
7, 8,
9,
10,
11? Okay.
12,
Okay.
13,
14,
15,
16 absent. 17, 18.
present, ma'am.
Next number.
19,
20. Then 21. Number 21 absent.
22,
23,
24,
25, 26,
27,
28,
29,
30, 31,
32,
33,
5,
36,
36. Okay.
37,
38,
40.
40,
41,
42,
43,
44,
46, 47,
48,
49,
50.
51,
52.
53,
Okay. 50 present. 51, 52
54,
present.
55, 56,
57,
58,
59, 61,
62,
63,
Okay. 53 present. Okay. So absentee 16 and 21. Two absentees, 16 and 21. 16. 21 absent.
21 present, ma'am.
Okay. Okay, thank you.